Hi, everyone. Welcome back. Glad you're able to join us on, at least what in Toronto is a rainy afternoon, but we are going to learn some great stuff with Chris Maddison here as our guest speaker today. So Chris is an assistant professor in the Department of Computer Science and Department of Statistical Sciences at the University of Toronto. We were just chatting about the challenges of that first year of teaching, especially when it's online. He's a CFAR AI chair at the Vector Institute, a research scientist at DeepMind, a member of the Ellis Society, and a faculty affiliate, of course, at the Schwartz Reisman Institute. Chris works on the methodology of statistical machine learning with an emphasis on methods that work at scale and deep learning applications. Research interests lie in the study of Bayesian inference, optimization, and discrete search. And Chris was just recently awarded the 2020 Corcoran Memorial Prize. Congratulations on that, Chris. Great news. Prize is awarded to students in the Department of Statistics at the University of Oxford for outstanding graduate work, which is where Chris completed his DPhil. And previously, Chris was a member at the Institute of Advanced Study in Princeton, New Jersey from 2019 to 2020, completed, as I said, at his DPhil at Oxford. He was an Open Philanthropy AI Fellow and received NeurIPS Best Paper Award in 2014, and a founding member of the AlphaGo project, which received the IJCAI Marvin Minsky Medal for Outstanding Achievements in AI in 2018. So might be your first year of teaching, Chris, but you've obviously been at this research gig for quite a while. So really looking forward to this talk on the future of representation learning. All yours, Chris.
Okay, thank you, Jillian, for that wonderful introduction. This is a little bit of a weird talk for me. It's not actually directly about my work. Instead, it's about the work of other people that has been inspiring my work. For some of you, this might be a lot of review, but I hope that this is more valuable for the SRI audience at large, because my goal is really to give a kind of clear insight into why I'm asking the questions that I am asking with my group, and to give you a sense of what I think is coming in the world of representation learning. Okay, so let's see if I can. Right, so here's what we're going to talk about today. I'm going to start by introducing the concept of a representation and briefly reviewing machine learning. Then I'll introduce a simple game that I hope captures the essence of what is so challenging, both about machine learning in general and in particular the challenge of designing representations. And then I'll review some history and speculate a bit on the future. So there are many routine tasks that we would like to automate in the world. And so, for example, in the world of self-driving cars, it would be great if we could automatically locate and detect stop signs. Digitizing texts by hand is very labor intensive, but it has the opportunity to sort of democratize the world's knowledge. And optical character recognition is a technology that attempts to automate this process of digitizing texts. So one of the commonalities between both of these examples that I gave here is essentially our desire to automate some process of prediction. In the case of self-driving and stop sign detection, what we want to automate is the prediction of where and whether there's a stop sign in an image. In the case of optical character recognition, we're interested in predicting the text that is represented on a printed page. So machine learning is exactly the field that studies this problem. It exists at the intersection of computer science and statistics, and it studies the problem of automating predictions. In particular, in machine learning, we're interested in algorithms that learn to make good predictions from examples. Classification is one of the problems that we study a lot. And so I will mostly be focusing on that because I think it's very intuitive to understand. Here is the basic classification problem, the basic pipeline that we are interested in. So on the left is an image. It's a picture of a cat on the snow. And what we want is some kind of algorithmic procedure that takes this image and spits out a prediction, which in our case is this word cat. Okay, so we have an image on the one side, we have our prediction on the other that we're interested in, and we want to find this algorithm that takes us from one to the other. You might be wondering, if you haven't actually seriously engaged with the problem of automating this, you might be wondering to yourself, wait a minute, Chris, isn't this actually very easy? When I look at that cat, it just pops out at me. That is a cat, and it's clearly a cat. And classification of images anyway, might seem intuitively easy because you and I can solve it easily. So to get a sense of how hard it is to really solve this problem using computers, we need to first understand how computers represent images. So the source of much of our data that we work with in the real world is analog, but modern computers are digital. So if we want to interface our computers with the real world, we need to convert that data into a digital representation. What that means in practice is that we end up representing data fundamentally as a list of numbers. So let's look at this picture of a cat, which to you and I pops out as a cat. When you store this image in a computer, what you're really storing is a big, giant array of numbers, like that array that you can see on the right-hand side of this image. So when a computer sees an image, it doesn't see cat as a gestalt that pops out at it. Instead, it just sees a list of numbers. And I think that this can help you get an intuition about why this problem is so hard. Imagine if you had to classify not that picture that pops out at you, but instead a list of numbers. How well do you think you could figure out if a list of numbers corresponds to a cat? So I hope that gives you an intuition that for many of these kinds of problems that we're looking to solve with computers, we don't actually know of any simple solutions. And machine learning is the study of methods that construct predictions from examples that attempt to solve this problem. So in the case of classification, this means that we might be given, instead of a solution, a set of labeled examples. So for this cat detection example, you might imagine that we've been given a big data set of images that we know have dogs in them, and a big data set of images that we know have cats in them. And the goal is to take that data, those sets, and convert it into this algorithm that automates the procedure we're interested in. So you can just think of machine learning as a study of methods that turn data sets into prediction machines. Let's see what this looks like in a very simple example, the entire pipeline, so that we're all on the same page. Okay, and the sort of silly little example that I'm going to consider is classifying flowers. Let's imagine that we live in a world where there's two types of flowers, and we're interested in separating flowers that have pointy petals and flowers that have round petals. And suppose we've been given 10 examples. Here we have 5 pointy petaled flowers on the left and 5 round petaled flowers on the right. So what we want ultimately is to classify a new flower. Obviously, if we were given one of these 10, we would know whether it was round or pointy. We want to classify a new one, so we need to find some kind of automated procedure. The first step is to represent the data as a list of numbers. For flowers, let's use the following representation. For each flower, we'll have the first dimension count the number of petals that it has. So here, the flower on the right has 6 petals. The second dimension can measure the length of the longest petal. Let's imagine that's a length 2 for this flower. And the third dimension can measure the width of the narrowest petal. So here, for example, this flower can be represented with the list of numbers 621. So now once our data has been given a representation that is a list of numbers, we can interpret this representation as a coordinate in some high dimensional space. Don't worry about what that means. In our example, we can just think about flowers as living, in some sense, at a point in a 3-dimensional space. So here on the right, I'm visualizing an example representation of these flowers. So you can see that they've been mapped to a little point in space. I've also colored them, and the color here represents this label or this prediction that we're trying to accomplish. So I've colored them orange if they are round petaled and blue if they're pointy petaled. So our goal is to find a prediction algorithm that gets minimal error on future data, that it doesn't make mistakes when it sees a new flower. We have some examples of flowers embedded in our three-dimensional space. And so we can use mathematics to find a separating hyperplane, which you can just think of as, you can imagine rotating like a cutting board in space until all of the pointy petaled flowers and all of the round petaled flowers are on opposite sides of this board. We can find this plane using mathematics, using the representations of the data set that we've been given, and find a surface that separates orange dots from blue dots. And we're going to use this as our prediction algorithm. So what happens when we get a new flower, which here I'm showing, it's not really clear to me what this is. Let's see what our prediction algorithm says. So we're given a new flower. We compute its representation by measuring the length of its petals and the number of petals that it has. We find out where it is in representation space, and we go back to our surface that we constructed from the training set, and we ask, which side of the surface does this new flower fall on? In this case, it falls on the round petaled side. So we're going to predict that it's a round petaled flower. Okay, that's it. We've basically all done machine learning together in this simple little example. And it seems pretty easy. I skipped over all the math, but that seems like a pretty straightforward example. And in particular, it might have seemed like choosing the representation felt like a sort of trivial step in that pipeline. Unfortunately, the choice of the representation is typically the most non-trivial and critical choice that someone makes in a machine learning pipeline. You can think of it basically as the substrate on which machine learning happens. So to explain this, let's consider a simple game. So I've cooked up a silly little representation game that I hope will really drive home the intuition of why this is such a challenging problem to design representations. Okay, so it's a two-player game. There's player one who's called the representer, and player two who's called the predictor. The game starts by randomly placing colored points on the board. You can see that in the upper right. The location of the points on the board you can think of as the representation, and the color is the prediction that we're trying to accomplish. Now we're going to cover a subset of them, and you can think of the uncovered points, the ones that have not been covered up, as the training set. Those are the points that you're given that you're going to construct your predictions from. And the goal is using just the uncovered points to predict the color of the unseen points. Okay, but we're going to let our two players play the game. So the first player is the representer. The first player gets a chance to rearrange the board. If unseen points get rearranged in this move, they keep their color. So you can think of this as the kind of cup and ball game where you put a ball under a cup and move it around the table. So here the representer has rearranged the position of the dots on the board, including the unseen ones. The second player now is going to pick a vertical line, and that vertical line also will have an orange and blue orientation. So it'll say that orange dots are to one side and blue dots are to the other side. Then all of the points are revealed, and both players get scored on the number of correctly classified points. So let's count how many points they got right. So here, there's one blue dot on a blue side, so that was correct. And there are 5 orange dots on the orange side, so those were correct. But there were 4 blue dots on the orange side, which they got incorrect. Okay. I don't think the representer did a particularly good job. And since we've played one round, maybe we have a better sense of how to play this. Let's see if we can do better on a second round. So here's an initial placement of the board. The first player now has a clever idea. The first player is going to rearrange the board so that the second player can completely separate points. Okay, so we're going to make 2 stacks of points so that the second player can isolate all of the points from each other. Now the second player picks a vertical line. and oops, player one screwed up. So here, despite player one thinking they were clever by separating two columns of points, because they moved unseen points around without realizing what the underlying colors were, they accidentally made the problem much harder for player two. Okay, this is a cooperative game, but it still seems very difficult. And I think it kind of distills the challenge of machine learning. And the kind of questions that are interesting to ask at this point are questions like, can the players protect themselves against all initial positions? This is the kind of question that we ask in statistical learning theory. Another interesting question you could ask is, can player one ever ensure that player two gets a high accuracy? Or given a certain layout, how should player two, the predictor, choose the vertical line? Okay, now that we've been equipped with this little game, I want to go through a history of what we have done in machine learning as a field to solve the problem of designing the representations. Basically, how the player one can play the game to support player two. And I'm going to focus on 3 periods, okay? And this is a complete just so story. And then the 3 periods I will call the feature engineering period, the deep learning period, and what I think now could rightfully be called the representation learning period. And I'll tell this story through 3 milestones that I think serve as events that herald a paradigm shift. I want to say a few things about this before I get started. The name of the periods reflect what I think the dominant technology or interest is, and I don't mean to imply, for example, that deep learning started in 2012. I'm also doing something a little bit weird that my colleagues might not agree with. I'm distinguishing between deep learning and representation learning on purpose here, and I hope that that becomes clear towards the end. Anyway, all of these technologies are still used today, and they actually started much earlier than 2005. So this really is a just so story, and the truth is actually much more complex than this. In the first period, the feature engineering period of our field, representations were designed by researchers, by people like me, and predictions were performed by machine learning, justified typically by elegant mathematics. And this was really I would say, the dominant approach from prehistory, which in my consciousness starts in the 90s, to 2010s. And really the way to think about this is that with feature engineering, there's a human in the loop for the representation design. So you can think of this as saying player one, the representer, is a human, and player two is the machine learning algorithm. So one of the very, very successful methods to accomplish this, this feature design is what in computer vision is known as the histogram of oriented gradients, or HOG. It's a very successful method. It dates to the 80s, but really became popular in about 2005. Here's the basic intuition behind the method. For an image, we're going to take an image and we're going to cut it up into patches. And for each patch in an image, we're going to calculate local color changes, differences in intensity and color values. And then we're going to represent the patch by binning which gradients occurred in the patch. And so what you end up getting is a representation that looks like the picture on the very right here. So we have this input image of an astronaut. And on the picture to the very right, you can see that these patches are being represented by gradients of different orientation and magnitude. And we're basically calculating how often different orientations and magnitudes occur. This kind of approach is really, really powerful, even when you pair it with simple machine learning predictors. These representations remove a lot of nuisance information. Because they're computing gradients or differences, they remove a lot of this sort of absolute information of color and intensity, and instead replace it with relative information of changes locally in the image. And so they extract kind of local smoothness, and they allow you to detect edges very efficiently. And so, in our little flower example, you can think of the pipeline now as including a step where we take this image, where we previously represented it maybe as a list of a few numbers that correspond to colors and intensities. And now we're going to change it into a list of numbers that represent local smoothness or the local changes in color. And then we can feed that representation into the typical machine learning algorithms like the one I described at the very beginning of the talk. So what are the characteristics of this feature engineering approach if we think of it as an approach to representation design? Well, first of all, it's in a sense multi-use, right? One feature design, which was typically published in a paper, could be used for many downstream tasks, at least within the domain that it was studied for. On the other hand, it typically had very limited expressivity, because if you think about it, these representations really are bottlenecked by the cleverness of researchers. And every new problem needs new features, or so it seems. And it doesn't really scale with the amount of data and compute that you have. So the quality of the feature is somehow fixed, and like I said, limited by our cleverness, and cannot really improve if you're given more data and compute. By the way, just as an aside, some of these things might have been slightly controversial to say even 20 years ago. So it's interesting how far we've come as a field that that's not really so controversial anymore. Okay, the second period that I would argue became dominant in early history, in recent history anyway, is deep learning. And to overcome the issues with feature engineering, for example, the limited expressivity and the fact that those methods don't scale with compute and data, it's sensible to ask whether we can also learn the representations using machine learning. So deep learning uses neural networks to learn the representation, and you can think of it basically as training both player one and player two jointly in the game. Neural networks are stacks of units that extract the representation, and algorithms for fitting neural networks are incredibly effective if you have a lot of data. So the way you should think about it basically in our flower example is that the flower gets converted into a list of numbers, which is a kind of initial representation. And then it's fed through this network of interacting units that modify the representation, and then fed into some final predictor that looks a lot like the predictor we already studied. And you can maximize the probability of the correct prediction jointly over the parameters of the network and the predictor's parameters. You can also sort of think of this as an iterated version of our game, where there's a rearrangement made by the neural network of the representation, and then a prediction by our predictor, player two, and then a rearrangement by player one, and then a prediction by player two, and so on. If you read it this way, it's really not clear that this process should work at all. I mean, in particular, player one doesn't really get any additional information from player two. And how does it get around the problem that we looked at in the second round that we played at the beginning? How can it do well on unseen points? So actually, at the time, deep learning faced extreme skepticism. And it really was 2012 where there was this sort of breakthrough. In 2012, this is the story of ImageNet, which was a very challenging image classification benchmark. And here at U of T, Alex Krzyzewski, Elias Sutskever, and Jeff Hinton were the sole deep learning submitters in this yearly classification challenge. And the results that they got were essentially impossible to ignore. So this, unfortunately, I can't quite point. I might want to point here. Sorry. This plot completely blows my mind, and I want to drive home this moment in history. So this plot shows here on the x-axis the year. Here's 2012. Can you see my cursor, by the way? Yes. Here's the year 2012. This is the accuracy, sorry, this is the error rate on ImageNet, that benchmark. And you can see that the teams in 2010 and 2011 were distributed, but sort of evenly distributed between a range. And here in 2012, this pink dot was the submission by the researchers here at U of T. And all these other gray dots were submissions by other computer vision researchers at very top computer vision groups. And they were all basically hitting a brick wall at about 25% error. And in 1 year, Alex Krichevsky and Ilya and Jeff basically broke through that brick wall and achieved 15% error. This was so extreme that it basically changed the field overnight, at least of computer vision. And then you can see that every following year, we got huge performance gains, and all of the teams basically collected on this deep learning approach and started moving together towards very strong performance. So the results were genuinely impossible to ignore, and deep learning is now the dominant technique for many challenging AI tasks. Okay, so what characterizes deep learning as an approach to representation design? Typically, it's a single-use procedure. So that representation, which is this big, horrific neural net, is typically trained jointly with the predictor, which means it's typically single-use. And even today, after 10 or more years of huge research effort into making this pipeline easier, it still will probably require somewhere between 1 and 6 months of real expert time to make progress on a new problem that you have not built a neural network for in the past. On the other hand, it's very expressive. The representations that are learned by deep neural networks are very, very powerful, and performance of the whole pipeline is typically much, much, much better than simpler approaches, with some caveats, which is that you need to have enough data and compute, which leads to the third point, which is that this approach scales. This approach to representation design scales with the amount of compute and data that you have. And this is a really critical distinction between this and feature engineering. Okay. So I want to speculate and think a little bit about what the future holds for representation learning by starting with the third period that I think is sort of beginning now. And at this point, we're sort of maybe getting into delusions of grandeur. And the caveat here is, of course, that I can't really see the future. But I think there's starting to be a paradigm shift in how machine learning, or at least people doing deep learning, what their interest is and the focus of the research is. And I think that representations now are themselves becoming the objects of machine learning in a way that is not new at all. Many of these ideas that are now succeeding have been studied for 20 years, but what is new is the scale and the impact of these ideas. And so the basic question that we're interested in asking in this sort of what I'm calling representation learning period is, can we learn the representation before we see the prediction problem? In particular, can we train player one by itself? Can player one make moves that will help before we even know what the prediction problem is? So I want to explain just a little bit why I use this distinction between deep and representation learning. Typically in our field, I want to be clear, these are used interchangeably, but I want to draw a distinction because I think there's something slightly different happening when we treat representations themselves as the objects of machine learning. Okay, so there are a couple approaches to this, but one of the common design philosophies for works of this type is to train the representation on what we call a pretext task. So that basically means training the representation without the label that you are eventually interested in predicting. One nice, really simple approach to this is the SimClear approach, which is visualized here on the right. And the basic way to think about this is that we're going to take our data point, we're going to apply a kind of random augmentation to it to produce two views. So here I've taken our flower and I've zoomed into one corner on one view, and I've flipped the colors on the other view. So I've produced two random views of my underlying data point. Then I'm going to pass those through the same neural network. So compute their initial representation, pass it through these units in the network to compute the representations that that network would use for those inputs. And then I will try to maximize the similarity of the representation for those two distinct views of one underlying data point. And so in this way, you can see that it's given some task which doesn't rely on those labels that we eventually want to make predictions from. This I'm going to talk about a specific instantiation of this generic idea of a pretext task, which I think is extremely exciting. So this is the contrastive language image pre-training, otherwise known as CLIP. And it's a specific choice of these sort of augmentations that I described. And here, the goal is to maximize the similarity between the representation of an image and its caption. Okay, so instead of having two image views, we're going to take an image, match it with a caption that it was paired with on the internet, and so here on the right, you can see the diagram of the flow of information. So we're going to take the caption and the image, and we're going to pass them through a network, which is here called an encoder, both the text and the image, which is going to produce a series of representations. And our goal is to match in representation space the images with their corresponding captions. Okay, so the goal is essentially that the representations extract information from images and texts that allows you to pair them together. You can sort of think of this in that previous view as saying that captions and images are two views of some underlying abstract concept. So here's a puppy on the grass and the text, Pepper the Aussie pup. And so you can think of those two as being two views of some underlying abstract concept of puppy. And this model, the CLIP model, was trained on 400 million image text pairs collected from the internet. Okay, so now I'm going to go through some of the results that this model achieved, which I think are genuinely stunning. The first is what they called zero shot, their zero shot model. So here they asked the question of whether we can construct a classifier for ImageNet without seeing any ImageNet labels. So this classifier was not trained on any ImageNet labels, and it was simply a byproduct of this pretext task procedure that they used to train the underlying encoders. And here's how it goes. So we're going to basically take our ImageNet labels, which include things like, maybe it's better if I point here, actually. We're going to have ImageNet labels, so things like planes, cars, dogs, birds. And we're going to construct a caption prompt for each of these possible classes. So we're going to construct a caption that says something like a photo of a dog. Now that we have the class in natural language, we're going to pass it through the text encoder, and we'll get representations for each of the n possible classes that we're interested in predicting for this image. Then we'll pass the image through the image encoder, get its representation, and compare it with each of the representations of the classes that we embedded. And we'll just return the class that is most aligned with the representation of the image. Okay, they didn't do any additional training. Here, they simply used the image encoder and the text encoder that came from this simple pretext task. And something that this was an exciting paper, but they didn't, there's sort of connecting this to the historical results on ImageNet, I think really highlight how amazing this result is. But they outperformed AlexNet without seeing any ImageNet data. Okay, so in less than a decade's worth of work, they now have a network that is able to perform as well as the network that kicked off the deep learning boom, in fact, better. And this network does not see any data of the ImageNet data set. That completely blew my mind when it came out. So they did obviously much more detailed analyses. What these plots are showing are the performance of this zero-shot model on a huge variety of downstream data sets. Okay, so in the first column, this first figure, you can see the relative performance of their zero-shot model against a model that was trained on ImageNet and then used to make predictions on other data sets. And you can see that they outperform by almost 28 points on some data sets, but underperform on other data sets. Then on the right, and so the more green it is, the better you are. The more blue it is, the worse you are. On the left, sorry, on the right-hand figure, you can see the performance of different models as you give it more and more, I'm going to be pointing at this, as you give it more and more labeled training data. So here on the x-axis, we're giving it more and more training data. This is their zero-shot model. This is a model that didn't see any data from these data sets. And it's basically outperforming other representation learning methods that see 16 labeled training examples. I think this is pretty incredible for me. Okay, so there are many questions that are asked in the paper. Another question is, okay, in that zero shot, they were testing both the quality of the representations as well as the quality of their text encoder. You can also ask the question of whether the representations themselves are high quality, and you get even better results. So here they're training a simple predictor from CLIPS representations and comparing it in terms of accuracy against the representations learned by an ImageNet model. And you can see that it's outperforming in almost all the data sets because you have more green bars. Another very interesting question they asked was the robustness to distributions shift. So they asked whether these representations were robust to changes in the underlying problem that we're interested in studying. And so here they trained a simple predictor on ImageNet from CLIPS representations and compared accuracy on other non-ImageNet prediction problems. So they're testing the transfer learning ability of these representations. So here, the way to read this plot is on the x-axis, you can see the score that they achieved on ImageNet. On the y-axis is their transfer score. So higher is better. And you can see that here in red, their best representations very significantly outperform the representations by other competing methods. Okay, so this is where it starts getting really wild. You can use these CLIP representations in sort of bigger pipelines to generate art. So basically you give CLIP a caption or a statement and use the text representation to guide the generation of these generative models. So here is an example where I pulled this from the Big Sleep subreddit. So the prompt that they gave CLIP was products from the 70s, 80s, 90s, Y2K era, and so forth. And it generated these pictures based on that prompt. I think these are disturbingly accurate. I can pull out the one that looks like it might have come from my childhood. This is Jabba the Hutt being interviewed by Jay Leno, also disturbingly accurate. Here's one that I made this morning, a utopia where AI makes the world a better place. And I think I can see SRI in the background. And then this one is truly insane. So let's see if this plays. This is AI talking to itself. So this is the famous GPT-3 model generating sentences that are then fed to CLIP, which is then used to guide the production of these images. So you can see like very clear concepts emerging here in these images that are produced by the representations that CLIP learns. All right. Okay, so what is this representation learning era, so to speak, as an approach to representation design? Well, I think this is combining all of the best of feature engineering and deep learning. So these representations tend to be multi-use in the sense that a single representation can serve many downstream users. They're very expressive because at the core, they're using neural networks, and they have performance approaching the sort of end-to-end single-use deep learning models, although they're not quite there. And they're more scalable, or rather, they're scalable in the sense that if you give them more compute and more data, this typically means you get better performance. Okay, so just to recap this just so story, in the early 2000s and before, we had a period of feature engineering and machine learning, which saw the construction of multi-use features, but with limited expressivity that were limited by the cleverness of researchers and which didn't scale with the compute and the data was available. Then in the last 10 years, we've had this explosion of deep learning research, which for the most part has involved sort of single use study of the training of a single model and the performance of a single model. This is very bombastic, but essentially unlimited expressivity. And in particular, it's scaled with the amount of compute and data that you had. And I think now we're entering a phase where we're really starting to look at multi-use representations that are very expressive and that also scale with the amount of compute and data that's available. Okay, so in the last 5 minutes, I want to go through one possible scenario that I hope will help, let's say, organize the discussion. Okay, so this is mostly, I want to pose a scenario and then put out questions, some of which I have thoughts on and some of which I am not an expert in and would love the thoughts of the SRI community. So here's a scenario that I think is implied by this vision of the future. What I'm imagining is that at some point, a firm will offer the following kind of service. Clients will arrive with a machine learning prediction problem, and they'll usually arrive with a small data set. Let's say I'm a startup that wants to do a Shopify recommendation system tailored to some type of user, and I have a small data set of labeled products with something I'd like to predict about them. But I can't afford a big data set. I can't afford a deep learning expert, and I can't afford the compute to train deep learning models. This firm will take this machine learning prediction problem, along with details of the type of thing you're trying to predict, the amount of data and compute that you have, and then license an appropriate representation that they have trained on some proprietary pretext task. And then the client will take that representation, fit their predictor using something cheap like scikit-learn on their own data, but using the proprietary representation of this big central firm. I think with the view of representation learning that I just described, this kind of relationship is now economically viable. Why? Well, deep learning is still not sated in terms of the amount of data and compute that it could possibly use. Big models may be much, much better than small models. We have reason to believe that. And we're not at the end of scaling yet. Today, to train the biggest models that are available to us, you really have to be one of a handful of very, very wealthy firms. And so only the wealthiest firms today can afford to train the best representations. And if compute scales 10 times, they will still be able to take advantage of that scale and produce even better representations. On the other hand, I think there's a huge number of small firms that could benefit from these representations. Okay, I think it's already also happening, which is why I feel somewhat comfortable in predicting this. So here in Toronto, there's a startup called Cohere that is essentially doing this, but for natural language processing representations. They have their own versions of BERT, and they're licensing those representations. So I want to consider the implications of this scenario for different stakeholders. First, the one that's nearest and dearest to my heart is, what are the implications for academic research? Well, I think this implies some critical questions for theory and practice. The first question is, and this is sort of the most obvious question, I think, which is that how should the pretext task that you designed relate to the downstream tasks that you want to do well on? Some theory exists for this, but I'm convinced that the paradigm is still unclear. We have some work in my group showing that invariance is possibly part of the story, and I could dig into that in the question period if people are interested in. The second question is, how can we practically improve the methods for this representation learning from these pretext tasks? And recent improvements on CLIP indicate that, yes, we can make improvements on this. I think there might be implications for the economy, but I'm not qualified to say this for sure. It seems to me like this kind of dynamic might accelerate the distribution of high quality automation and democratize the gains of deep learning even further. With powerful representations, even the simplest of predictors, things that any third year undergrad, after having taken our course in machine learning, could use from scikit-learn, that these predictors can achieve remarkable performance. I think it also has many implications for the question of robustness and fairness of our machine learning models. If you think about it, having a single representation for many tasks allows us to amortize effort. We can focus on that bottleneck in the pipeline. So I think it makes it financially viable to begin asking questions about whether we can certify, regulate, or audit representations. So for example, we might be interested in improving the robustness under adversarial attacks for all downstream tasks, not just a single task. We might be interested in improving the invariance of a model to sensitive attributes like race or gender for all downstream tasks, not just the one task that the model was trained on. And by the way, I think these are also risks in this approach, which means that if we don't have this kind of view into the representation, if the provenance of the representation or the data that was used to train it is not transparent as it is currently at places like OpenAI, this exposes us to a risk if we use those representations without additional information. Some theory exists to describe when these kinds of things are possible with respect to robustness and fairness, and including some work my group submitted to ICLR. And then finally, I think there's all kinds of interesting legal implications for this vision. So the question that I'm sort of interested in is, well, if we now have multiple parties collaborating to contribute to the final prediction of some machine learning pipeline, who is liable for that prediction? Is it the large firm that trained the representation model, or is it the small firm that used that representation to form predictions? Okay, that's it. Thank you.
All right, thank you so much, Chris. So Jillian had to go to another meeting, so I'm gonna be managing the Q&A and I'll be monitoring the chat. So Kelly, would you like to get us started with questions?
Sure, I would love to. Oh my gosh, Chris, that was an absolutely fabulous presentation from start to finish. Everything you wove through. Anyway, I'm sure everyone is thinking the same thing. I'm just buzzing. Your enthusiasm comes through. So it was just brilliant, brilliant.
Thank you.
I have no questions. No, I'm kidding. I have a question. I have a few actually, but one is, so you presented the three phases in the story as sort of replacing one another, but it's sort of, are there not applications or environments where feature engineering might still be a better solution, or a more have some benefit to still provide?
Yeah, that's a great question. Yeah, so yeah, absolutely. It was definitely a just so story. I mean, neural networks and deep learning have been studied for much longer than, much before 2012. And one of the things that we tell our students in 311 is that the first thing you should try is something like a random forest predictor. So you shouldn't just jump to your neural net because everyone's talking about deep learning. You should kind of use the old tried and true methods as a first pass. And so absolutely, there are problems today that people care about that that we can solve with the machine learning that we knew about 20 years ago. I guess it's hard to characterize exactly which problems fall into that domain and which problems fall into the domain of deep learning. But I guess typically speaking, if you have lots of data and the prediction problem that you're interested in has sort of low-ish noise, but very complex structure. So this question of predicting class labels of images is something like that. Then you're typically want to do something like deep learning. On the other hand, if your problem has a lot of noise in it and you're just sort of trying to control the noise, but the structure in it is somehow simple, then you're better off with simpler methods. I sort of think that in a way, these representation learning methods might kind of unify everything in the sense that you can think of them in a way as turning that hard problem of structure into one where in the representation space, the structure is simple. Yeah, so that's it. Yeah, but yeah, you're right. Absolutely. It's still useful today. They're not replacing each other at all.
Thank you. you want me to ask again, Beatrice?
Yeah, I mean, go ahead. And if others have questions, please do raise your hands and I will call you.
Okay, great. So I love the scenario. I love the questions. I love that you pose things to the community. So one of the questions I was thinking about even before you did that was, if you could assemble your dream team to make your scenario a reality, what roles and expertise would you, I mean, obviously legal and economists and so on, but what are some of the other roles you think would need to be at that table?
Yeah, so one of the roles, I guess I'll say, the first role that came to mind is the role that I am least good at, which is data cleaning. So the CLIP paper, by the way, like the CLIP paper is a wonderful paper, I think. I think it's a great example of scholarship. They're humble about what they can say, but the result is just this like litany of impressive results. One of the things that they don't do a fantastic job of, though, is being fully transparent about what it took to produce the data that they trained their model on. And my understanding through secondhand sources is that the preparation of the data was incredibly important to the quality of the model. And so this involves, making sure that the data set is balanced, that you didn't accidentally, you thought you had 400 million images, but actually half of them have a silly caption that is the URL or something like that, right? That's a very silly example that you could avoid, but there's all sorts of subtle ways in which the data can have a lot less statistical structure than what you're actually interested in. And so, and just to like put a finer point on it, this whole pipeline only makes sense if there's actually a connection between the pretext task and these downstream tasks. And so the quality of the data for that representation is critical, and it will sort of reverberate in the quality of all the downstream predictions. So the first dream team person would be someone who really understands data cleaning. This is something that I don't really know much about. And I think, at least when it comes to representation learning, is actually an important, it's a very important research area. I think there are things to be discovered and things to learn about that well, at least I don't know anything about. So that's one. I guess the other obvious answer is someone who's very good at deep learning. And I think, it's also an exciting place for someone who's a little more theoretically inclined to interact with someone who's more applied, because at least in the experience of my group so far, there has been a nice interplay between ideas and theory as we've been developing some of the theory, feeding into specific applications. And so I think there's a role for theorists as well in one of these dream teams. I haven't thought that much about preparing this firm yet, so maybe in a year I'll have better answers.
Great, thank you. And I see Sheila's hands up, but just quickly, one role, and I don't even know if it's relevant, but in a previous life, I worked at IBM and I was in charge of benchmarks for the database product, DB2, and there's a lot less uncertainty in that world, but we did have a really strict auditing process for the algorithms, or when we ran a benchmark that would be probed and tested to make sure that we hadn't cheated somehow in the benchmark. Anyway, just a thought.
Yeah, no, actually, sorry, I'll let Sheila right after. Yeah, I totally agree. So one of the big themes in deep learning, one of the big challenges is that when these projects get to this kind of scale where you where it's sort of modular and there are many parts, one feeding into the other, you can accumulate what's called, I guess, technical debt, where a small failure at the beginning has this kind of cascading effect, and it's typically expensive to run the full pipeline. So you need proxies to tell you, whether or not you think you're doing well early in the pipeline before running the whole thing. And this has shown up in big projects that I've been in, like in the AlphaGo project. This was important at different points in time. And I totally agree. So understanding how to minimize this technical debt in a pipeline through benchmarks and things like that is another very important part of actually building these things in practice. Yeah, absolutely. Thanks. Okay, Sheila.
Hi, great talk. I echo everything Kelly said. It was really great and inspiring talk. The very first thing you said on your sort of reflective slides was exactly what I want to ask you about. I'm wondering about how important the knowledge of the distribution of downstream tasks is fundamentally to this aspiration in the long term. And in particular, maybe related to that, what is a good representation? I know sort of one of the criteria that you were using was this notion of multi-use, and I think that's important. But sometimes multi-use comes at the expense of some other things that we care deeply about. And I'm wondering if you can comment on that trade-off between, task-specific versus task-independent representation, and how without knowing that distribution, we're ever going to be able to verify or license or do any of those answer any of those other great questions.
Right. Okay, that's a great question. So maybe I will sort of share. Yeah, I think the short answer is that I'm not proposing anything magical here, and that essentially you're going to have to lose some information. And the question is making sure that you only lose the information that you didn't need. So let's see if I have something concise here. Essentially, right. Okay, this is a good example. So in one of the papers that I alluded to, where I said that invariance may play a role, we sort of follow the thread of this, exactly the question you asked. And what we show is that we characterize essentially the amount of information that you can remove from a representation if you want to be able to still guarantee predictive performance on a big set of tasks in the future. And in particular, what you need to know is essentially the equivalence classes of the input that keep all of those downstream tasks invariant. Okay, so here's an example. So here is a two-dimensional distribution. So imagine when you ask from a draw from this distribution, you get some point that pops out, and you want to predict something about different points in space. Well, if you wanted to sort of store this distribution in a computer, you would do some kind of quantization, and you could represent it with these little dots here. So you could come up with a discrete code that represents this continuous distribution. And let's say you wanted to predict something about the outcomes of the distribution, but for some reason you knew that you only cared about tasks that depended on the length of the vector that came out. So this is a two-dimensional point in space, so it has a length. Well, then this representation in the middle would be very wasteful, because you're storing more than just the length. You're also storing rotation information. So in this paper, we basically give a characterization of the optimal bit rate that you can get while removing invariant information. While removing information, that's right, while removing information that your label is invariant to. So if you only wanted to predict things that depended on the length, then you should come up with a code that looks like this one, where these circles are basically equivalence classes, where you say, I don't really care where I am in the circle. I just want to know which of these circles I'm in. So basically, it's about understanding how tasks relate to each other. And I just want to follow up by saying something about, let's see if I can, what's a good example? So maybe, so this is why I'm so excited about CLIP in particular, because I think the point of view of invariance as far as CLIP is concerned is basically that this representation is learning, this encoder is learning an image representation that carries in it something like all and only the information that would be contained in a caption. So basically, any downstream task which you could solve knowing only the caption of an image, you can solve using clips representations. And I think this point of view is much more powerful than some kind of hard enforcing of invariance, because it's sort of saying, I know that there is invariant relationship between two types of tasks that I have data access to, that I can like sample draws from a distribution from. That's much weaker than saying, I know it's rotation invariant, for example. So I think this is an example. I think CLIP is exactly an example of something where it's restricting the set of tasks to classification tasks, but that's still a very big set. So yeah, I think that's sort of the summary. I could keep rambling, but.
And is it classified? So the interesting thing to me is it classification tasks over the vocabulary that's been prescribed by the caption?
Yeah. So there's
or prediction. It doesn't even have to. I would relinquish classification. That somehow the vocabulary is constraining the family of tasks that you're going to ask it to do downstream, and in a way maybe that's somehow like defining a set of features. Right.
I don't know. I have a lot of thoughts about this. By the way, I think this text encoder is exactly where all of the bizarre magic happens. And I think there is still a lot of unexplained magic happening in CLIP. In a sense, I agree with you that the text somehow limits the set of concepts that you can represent. But I don't think that the vocabulary necessarily does, or it necessarily limits what is in the representations of the image encoder. But it might just be a subtle distinction. I think at the end of the day, it will be able to, the representations will allow you to predict things that are sort of in bijections with possible sentences. I think that I would be comfortable saying. Yeah.
I have a follow-up, but I'll ask you offline some other time. Thank you.
Okay.
Interesting.
Thank you. So we have a couple of questions in the chat. Mohammed and Tegan. Mohammed, would you want to ask it out loud to Chris, or I can read it if you prefer?
Sure. I can go. Thank you a lot, Chris, for the amazing talk. So I couldn't help but notice that what the CLIP is doing, maybe that's my understanding, is that it's subsuming some ideas from multimodal learning, right? So you have one modality, which is the text, and then you have the modality that is the images. And then what it's really exploiting is that there is a strong correlation between these two, and that's sort of gives you, a very good representation in the sense that, if you have some nuisance correlations, then it will be just so much less likely to happen both in text and in image, right? So that is essentially removing a lot of those unnecessary information. Would you agree with that? And if you do, as a follow-up, do you think it also stands to reason that this scales in that dimension as well? So if we have more modalities of data, for example, for autonomous driving, it could be LiDAR sensors, image sensors, some, I don't know, audio, if that's ever a thing. But we know we can build more sensors and more sensing. I just want to know your thoughts on that.
Yeah, I totally agree with everything you said, basically. So the first thing that comes to mind is there was a paper out of DeepMind that was led by, I think, Aaron van den Noord, who does a lot of work in this area, where they learned audio representations of that were trained from, I think, YouTube clips or something, or video. So they had the video stream, the spectrogram, and the waveform as three modalities that were fed into a sort of three-way version of this clip thing, and it improved the audio representations. The second thing I want to say is that, I mean, one of the things I've been dreaming of doing here, I think self-driving cars have, I think, something like 6 different, typically six different data streams, including LiDAR. I think it would be so cool to train a representation by letting those 6 modalities essentially supervise each other in something, in the setup sort of like CLIP. And the way you should think about what these contrastive learning methods are doing, I think, is basically like intersection. They're sort of like intersections of information. So they're saying, take the information that is common to the text and the image. In the case of text, I think in the text and images, I think text carries somehow less information than the image. It's like a strict subset of the information in the image. Maybe not with Pepper here, but in any case, I think it's like an intersection operation. So you have to, the one downside that I foresee is that you might end up getting rid of too much information, but I think it might be a cool way to do some kind of signal separation if you have multiple modalities. That's it. Yeah, basically, I totally agree. I think there's a lot of opportunity to do all kinds of mishmashes here.
Wonderful, thank you.
Great. Next, we have Tegan. Tegan, would you like to read your question out loud? I think you're muted.
Sorry, I can read it out loud. Or I can sort of summarize it. I don't know, Chris, you probably have enough time to glance at the chat, but basically, I think my question sounds kind of adversarial, and I said I'll be playing the role of a grumpy, skeptical person who thinks deep learning and representation learning are the same thing. But I appreciate your perspective on this and your definitions. I'm not trying to be as argumentative as this might sound. So the questions that I want to ask are two. One is, can you convince me why prediction of a categorical label was ever the right specification for, we have this cat and we want to know that it's a cat? That seems more like identification than prediction. Like, why is prediction the right specification for identification, and why did that ever help? And then in this timeline, the just so timeline that you proposed, now that we're in this phase where we're not doing prediction anymore, like, can you convince me that we're not actually doing prediction anymore, and that the pre-task is not a prediction task? Isn't it just like a recategorization or a different type of prediction that provides more information than a label did?
Yeah. Okay. Sadly, I might disarm you by just agreeing with both of your points. So, okay. First of all, is prediction the right? Well, I guess I didn't fully understand the first question, but I'll answer the question that I understood, which is like, or I'll give you a perspective on that, which is like, why did we care about calling this a cat? Like, who woke up and made that the most interesting problem that we're interested in? And in particular, who told us that ImageNet categories were the 1,000 most important categories in the universe, right? Nobody. And I think that actually highlights, no offense to my colleagues in community, how absurd some of our benchmarks are, right? Like, they don't really track what we care about in the real world so much. Like, what they do track is, if someone came up with the 1,000 most relevant categories, we now have algorithms that we believe would do a good job of predicting those 1,000 most relevant categories, but like, none of us really believe that the 1,000 categories of ImageNet are actually the ones we care about. Which is why I'm actually so excited about the representation learning stuff, because it's hard to argue against pairing captions with images, right? Those are like genuine in the wild relationships that humans produce unprompted. And I think learning to pair those is actually more of an essential problem than ImageNet by itself. And so I'm very excited about the idea, and similar with that multimodal answer, like, I'm very excited about the idea of going to the real world and finding data that has co-occurred naturally, and asking and discovering within that supervision problems. Which leads me to your second point, which is that, isn't this just prediction under the hood? And I didn't want to go into this because I thought it would confuse people, but I think the answer is basically yes. I think this is a different kind of prediction. You can really, and I actually think if you were to sit down and do the theory, it makes more sense to talk about this as you are training a predictor that predicts from text the most likely image, and from images the most likely text. And these are somehow being trained jointly. I think there are a couple distinctions in the representation learning world that the reason I felt comfortable pulling this apart is twofold. One, the predictors are not often explicitly instantiated. I think they actually exist. They're kind of like implied by this contrastive or self-supervised learning method that you construct. And the second reason that I felt comfortable pulling this out is that I think this idea of there being multiple possible downstream tasks on which you will perform well, that idea is sort of, it's not really even honestly new, but it's sort of like working so well now that it's important to think of this as being a distinct problem from just the like very standard statistical learning theory. We have a hypothesis class and we're just looking for a predictor style problem. I think this is now a question of reusing predictions, reusing what you learned on one problem, which is the pretext task, on future tasks. And I think that is becoming kind of a more important point of view than the kind of atomic statistical learning theory, you're selecting a point from a hypothesis class point of view. That's it. So yeah, basically I totally agree with you.
Cool. Yeah. Quick follow-up about the hypothesis class thing. Like, what do you think on the hypothesis class side, like the statistical learning theory, statistical mechanics, math, that talks about finding the right hypothesis class, maybe, instead of finding a point in the hypothesis space?
Oh, sorry, I didn't fully follow the, so.
Yeah, that's really free, sorry. We have been in machine learning up till now doing a lot of looking for a point in hypothesis space that best fits our training data or maybe best generalizes to a specific test set. But what we're doing now already with representation learning and multitask learning is looking for an area of hypothesis space, not so much a point. And I don't know, do you think so? What are your thoughts about that?
I don't, at least in the way
that can look optimized for this space being good instead of a point, finding a good point in this space.
Right. At least in the categories that I think of, I'm not sure I would totally agree that we're changing the hypothesis class. I think the way I think about this is that statistical learning theory is incredibly pessimistic because their statements have for all quantifiers. So they want an algorithm that works for all possible input distributions, which is too ambitious. That's horrifying, right? I mean, you can come up with the most horrifying input distribution. I think the way I see representation learning is that you get a step in between. You get to say, I have some additional knowledge about my prediction problem, and that is either through knowledge of invariance or knowledge of a related pretext task. And now I get to structure the representation space. I get to make changes to its geometry and so on, so that when I eventually get my data set and do kind of like linear readout or something, when I eventually get my data set, my downstream data set, I can protect myself because of what I did given some initial knowledge. So it's like you get a step in between the quantifiers that not many people have fully, there's some work on that, on exactly that question, but like, I don't think that theory has been fully fleshed out.
Right. I'll settle for now for the technical term of horrifying.
Yeah, exactly.
Alex has a question.
Yeah, good talk. I really enjoyed listening to it. Do you have any thoughts on like how currently everything is like very unstructured, where like transformers are very like flexible models and representations are just this vector of value or continuous values? Do you think there's any benefits or maybe no benefits to maybe building more structured models or more structured representations, maybe not in the sense of like modalities, but I feel like concepts that we're interested in modeling, especially when we're slamming together all these really big modalities, concepts might benefit from like being separated in a structured way. Does that make sense? Or is that maybe something that is just, yeah.
Yeah, I mean, I think it's a great question. The question makes a huge amount of sense to me. Okay. This is a question that's near and dear to my heart. I will tell you what I want to be true. What I want to be true is that structure matters, and that if you know it, you should put it into your model, and you could do a lot of cool math on how to impose structure on neural nets, and there's a lot of fun stuff and cool papers we could publish. In my experience, if you bet against just making the neural net bigger and getting more data, by being more and more, by you being clever and imposing structure, you're always going to lose out, sadly. So I think if you're in a regime where you have just huge amounts of data and huge amounts of compute, the fully unstructured sort of neural goo approach is just somehow always going to be better, because you're not constraining it by your presupposed intuition about how the problem should be solved. Another theme that I think is kind of throughout this Just So story, which I didn't really say much about, is sort of like wherever the researcher can remove themselves from the solution that the algorithm finds, like that, which hypothesis it actually picks for the final predictor, it's almost always a better move. In other words, if you can just let the data speak for itself, if you have enough data and it's high quality, many caveats, then it's almost always better to just let the data do that. And I guess obviously in a low data regime, or if you really, really, really genuinely know the structure and it's actually there, you can probably exploit it. In this, I think there are also many questions in terms of how to exploit it. So in this view of contrastive learning, of the sort of invariance view, you can actually really exploit knowledge of the domain through your design of the invariances. So we have a project in our group that is looking at learning representations for integer programs, which have a huge amount of invariant structure. And you can just exploit it there by designing augmentations, for example. So part of the answer is, like, if you have data, it's often better to just let it speak for itself. But in some ways there are, I don't know, this is a very complicated question. This is an age-old question. And I think the whole field sort of bops back and forth between the different approaches. Right now, I'm sort of feeling like for the most part, you should just let the data speak for itself.
Great, thanks, Chris. Do we have any other questions? All right, so if we do not, I want to thank Chris again for this great presentation, and thank you everyone for being here. And I just want to let everybody know that next week we're going to have a talk by Marsha Chechik, professor and chair of the Department of Computer Science at the University of Toronto. And the title of the talk would be on safety, assurance, and reliability of software engineering perspective. All right, so thank you so much again for being here.
Thanks, everyone.